All right, so welcome everyone to this week's What Physicists Do. Today, it's my great pleasure to welcome Dr. David Ramirez. So Dr. Ramirez did his bachelor's degree. He double majored in physics and mathematics at MIT before attending Stanford for his PhD. He then did a postdoc at UC Davis before heading to Brown, where he comes from us currently. So thanks for coming us at the later hour today, where he again is doing a postdoctoral fellowship. So welcome, Dr. Ramirez.
Great, thank you. And thanks for the invitation and the wonderful introduction. So yeah, it's great to be back or at least virtually back in California, I should say. I miss it. But so today I'm going to tell you some lessons that black holes can teach us about superconductors. Let me rip off a couple of band-aids real quick here. When I say black holes, I don't necessarily mean the kind of astrophysical black holes that we are used to thinking about, or that have been certainly. There's been a lot of really exciting developments experimentally along astrophysical black holes. And similarly, when I say superconductors, I don't necessarily mean, pick your favorite cuprate or whatever. I mean, these are going to be kind of general lessons that gravity, and in particular black holes, can teach us about what I think we could call kind of difficult systems, or in some sense, they're going to be difficult. I'll be describing exactly what I mean by that. But yeah, so I think it's probably best to just start with an example. And so we're all reasonably familiar with, say, considering a gas at some temperature. Not necessarily, we don't need super detailed description. We just need to know that a gas has a bunch of molecules and they're all zipping around at various velocities. So these little points here are supposed to be molecules, and they're randomly distributed in this box, and they're all kind of going in random directions. And this is kind of the picture we have of a gas at high temperatures. And so what I'm saying here is that at sufficiently high temperatures for reasonable gases, say classical gases that we're familiar with, they're predominantly dominated by their kinetic energy. And so in my mind, I would say that this isn't so difficult because the fact that everything is pretty much kinetic energy, you can kind of start as everything kinetic energy, and then you kind of add little corrections to the fact that the gas also has some potential energy going on, but in the high temperature limit, it's not as important. And of course, conversely, we have that at low temperatures, our gas cools into a solid. I'm imagining here we're at sufficiently low pressure. And so again, this low temperature phase is reasonably simple in that it's also potential energy dominated. So here, when you have a solid, the molecules don't have such large kinetic energies as they do over here. And in fact, at zero temperature, they will have very small kinetic energies. And so this low temperature phase, which is a solid, like say ice for water, or for H2O molecules that we're familiar with. So the low temperature phase is often, potential energy dominated. And so I would say that both of these two things are, in some sense, simple. We have reasonably good techniques to understand the properties of these kinds of phases of matter. And so when I refer to superconductors as kind of difficult systems, what I really mean is that in some sense, there's kind of a competition between different things. Like the obvious example here that I haven't drawn in the middle is that we're very familiar with the fact that H2O molecules have more than just a solid phase and a gas phase, but in particular, there's a liquid phase in the middle that is not either of these two things. In some sense, in a liquid, it's both kinetic and potential energy. And so the quote unquote difficulty of certain superconductors, I should say, not all of them, is that there is significant competition between kind of, essentially the system is pulled in different directions and it doesn't really know which way to go. And often that's a sign that something even more interesting can happen, like say high temperature superconductivity or all kinds of other interesting exotic phases of matter. And so these generally fall under this umbrella of strongly interacting. And I tend to think that maybe competition is a slightly better turn of phrase here, but I think strongly interacting has a very nice, precise definition, but it's a bit technical that I won't go into. And so, as I mentioned, there are all kinds of different really interesting physical systems that I would say fall under this umbrella of significant competition or strongly interacting phases. And so a couple of simple examples here, as I mentioned, is high temperature superconductors. Quantum Hall effect is also a very strongly interacting phase of matter. But the kinds of techniques I'm going to be talking about throughout the rest of this talk aren't necessarily kind of specifically for the domain of condensed matter physics or many body physics. And in particular, there are all kinds of interesting high energy physics examples of strongly interacting phases of matter too. For instance, quark gluon plasmas that are created, in particle accelerators, or you could imagine in the early universe, shortly after the Big Bang, there's kind of a big soup of a bunch of stuff all strongly interacting at really high temperature. And so understanding those early universe plasmas is a theoretical challenge that, yeah. And similarly, things like neutron stars, kind of what you might call kind of the condensed matter physics of QCD or of the strong interactions. Say, when you have a finite density of quarks, then they can interact strongly and they do interesting things. We're not going to go into any of these applications in real detail. This will be very much a big picture talk. But what makes these phases of matter difficult is the fact that essentially our strategies for attacking problems don't really apply. So by and large, a lot of physics, I think in general, we feel like we have a pretty good understanding of some basic laws, or the basic laws in a lot of situations, but actually solving them for quantities that we care about is a very different question. And so here's kind of a sampling. I like to think of it as we have different streetlights, and we search under the different streetlights and see we have different techniques that are useful in different places. And so, for instance, this weakly interacting, you kind of might imagine starting with our high temperature gas and slowly adding in the effects of the potential energy in the gas. And you can kind of do, essentially it's what we just call perturbation theory around a simple point. Of course, we're sometimes lucky to have exact solutions. Certain problems are very amenable to numerics. Other problems, there are good approximations for certain things we care about. And okay, this one over here is going to play an important role today. And in fact, my goal for today is to convince you that in fact, there's a relatively recent, it's maybe 20 years now, so it's maybe not quite as recent as we might like, but we've essentially learned, we found a new streetlight, and we found that certain theories of gravity, so when I say certain gravities, I mean certain theories of gravity, they're slightly peculiar, and in particular, the gravity is not, it's not directly relevant for kind of our observational, say, astrophysics in our universe, but is a kind of a theoretical tool. What we've learned about these certain types of gravity is that, in fact, they can fall under this duality umbrella and give us some pretty strong quantitative control over some of these difficult phases I was mentioning before. And so this is a very bizarre statement if this seems surprising to you, because in particular, these strongly interacting phases I'm talking about have nothing to do with gravity whatsoever. So a superconductor in your lab I'm not saying that you have to worry about Newton's constant for your experiments. I'm saying that, well, in general, I won't say much about your experiments. So, but the statement is that certain gravities can tell us interesting facts about non-gravitational theories. And these non-gravitational theories, I would say, are interesting for other reasons. Great. So that was like my lightning overview of kind of the big picture of where we're going. And so super quick outline here is, first we're going to talk a bit about black holes. As maybe suggested by the title, they will play an important role today. And so in particular, when I say gravities, I mostly have in mind that I'm thinking about some kind of interesting black hole phenomena. And so first we're going to talk about black holes and review some, at least some statements that are pretty old about black holes, but it's good to know. And mostly this will be kind of a motivation for us to understand what is this new duality and what do we mean when we say that gravity is teaching us about non-gravitational physics. And finally, depending on how much time I got by the end, we'll see how many lessons I can teach you. Great. So again, caveat here, I am very much a theorist. Experiments and me do not go super well together. And again, I don't want to give the impression that to solve high temperature superconductivity, we need to think about black holes. But the moral is really that we can learn things that we can kind of general picture that helps us understand the realm of possibilities in a quantum system rather than, say, a specific instance of an interesting physical system. So with that disclaimer, let's think about black holes. And we're going to go back a few hundred years here. So I think it's kind of an interesting historical fact that apparently folks had thought about black holes in Newtonian gravity. And the basic concept is pretty simple. In our introductory mechanics classes, we learn about escape velocities, which are essentially, the question it's answering is, how much kinetic energy does a projectile need to escape the gravitational potential of the Earth? And so we can, this is a relatively simple problem that we can just solve in Newtonian mechanics, I should say. And so we imagine here, if we have the Earth, then we send some projectile and we want to send it into space. And if you just kind of play around with the Newtonian expressions for kinetic and potential energies, then you'll find that the escape velocity for the Earth is somewhere around 11 kilometers a second, which, okay, is pretty fast, but it's not too crazy. We can repeat this calculation with the sun. It's a much larger, or I guess, yeah, it's a reasonably larger escape velocity. But morally, there's nothing too crazy about these different numbers. And I think a curious fact that maybe I should have emphasized here is that this expression is independent of the mass of our projectile. This is the fact that the gravitational potential energy and the kinetic energy are both proportional to the mass of your projectile. So it'll cancel out in this expression. And so this led folks, in particular, led these two gentlemen. I don't know if I'm pronouncing these correctly. Michel and Laplace. I don't think that guy's French, but or this guy, I should say. But I don't know. So they asked the question: are there any physical scenarios where the escape velocity can be faster than light, faster than speed of light, I should say? I think it's curious, also historical fact, that they already knew at this point that the speed of light was finite through very careful astronomical observations. And so in the late 18th century, these two gentlemen came up with the escape velocity in Newtonian gravity. And I mostly just put this picture here because, man, this is quite a title for Michel's paper here. But yeah, so the basic notion here is there escape velocity that is faster than the speed of light? And they found exactly what the kind of how compact an object needs to be in order for that escape velocity to exceed the speed of light. And so this eventually fell out of favor because the wave theory of light was kind of taking off, and particle descriptions of light were not super popular. So people kind of tossed this out the window when they threw corpuscles for particles of light out the window. But we'll eventually, we'll see very shortly that essentially it'll take Einstein to come along and fix this fact. But before moving on to GR, I should caution you to not take this analogy necessarily too seriously, because escape velocity is escaping to infinity. So you're escaping the potential well of the Earth, which extends all the way to infinity. And so the escaping a black hole is much harder than escaping a black hole means you really don't get out of the center of the black hole. And obviously, I should mention here the really exciting picture that we now have of a black hole, so I can use that in this slide. Okay, so to get a little more concrete idea of how light and gravity interact, we had to wait for Einstein to come along and show us the way. And I'm not really going to use too much of general relativity. It'll be more pictures and kind of just some observations. So the first observation that Einstein had is that, in fact, light is affected by gravity. If someone is standing over here, this weird shape here is a weird disembodied eye. So there's a person observing, and they see that this light gets deflected because of whatever this massive object is. So probably some star. So Einstein told us how light is affected by gravity. The other super important fact that Einstein told us even before he figured out general relativity is that, in fact, the speed of light is the ultimate speed limit in our universe. So everything must be have a local speed that's less than the speed of light. And so from these two facts, I think we can revisit Laplace and Michel's construction and think about it again, but now, of course, in the realm of general relativity. And so, and in fact, shortly after Einstein published his work on general relativity, or I should say the final work on general relativity, his equations for general relativity, very shortly afterwards, Schwarzschild had found a solution to Einstein's equations. Einstein himself was pretty pessimistic that anyone would ever find any exact solution because his equations are quite complicated. But I guess I want to say Schwarzschild must have had nothing better to do, but he was actually apparently fighting in World War I at the time, which is pretty impressive to me. But what did he do? Well, he solved for what his equations would tell us is the gravitational field surrounding some spherically symmetric mass. So in particular, if we had some star here, then Schwarzschild would tell us what is the metric, or sorry, not the metric, what is the geometry, what does gravity look like in this region outside our star. Great. So this was, like I said, shortly, months after Einstein published GR. So this is I think I want to say published maybe early 1916, somewhere around there. And people were pretty happy with the solution. the solution is used for all kinds of important experimental tests of GR. For instance, this light deflection was experimentally observed shortly after, so I would say probably within 5 years or so of Einstein publishing the field equations. Some folks had set up an experiment to see the light deflected by the sun, but also this geometry that Schwarzschild found, or the gravity around some massive object, was also important for, say, computing the shift of the perihelion of Mercury, which again was just another important historical test of GR. So Schwarzschild solution was definitely super important and used a lot immediately after he found it, but I would say that it really wasn't until probably around the late 50s that people really started appreciating and thinking about, the fact that this Schwarzschild solution secretly has a black hole in it, or predicts the existence of a black hole, you might say. And so, what do we mean by a black hole? Well, we mean what Einstein has told us is that if I have an observer sitting, say, at the vertex of this cone here, and we ask, what are all of the possible trajectories that observer can take starting from that point? So starting from right here. And this picture is meant to tell you that he can only go into the blue region. So whatever trajectory this person is going to take, it has to stay within, at least locally, this little blue cone. The red cone is the past. So if you end up here, you have to have come from somewhere inside that cone infinitesimally before that. And so what I'm saying here is just that the boundaries of this cone are kind of as fast as you can possibly go. And we know that there is an upper speed limit because Einstein told us that the speed of light is our upper speed limit. So this horizontal axis is meant to be radius. I should have written that somewhere, but and so if you were to go outside the cone, you would be going too fast. So that's not allowed. And so that's kind of the origin of where these cones come from, is that you can't have a slope that's bigger in this picture than, I guess it's roughly 45 degrees or so. But sorry, you have to have a slope that is bigger than 45 degrees. But so Einstein told us not just that the speed of light is a speed limit, but also that it's affected by gravity. And so if we had some big massive object over here, there is a particular cutoff radius that we will be talking about shortly. And as light gets closer and closer to that cutoff radius, these cones start tilting so that no matter what you do, eventually you can't get back out to this outside region over here. So this cone is always pointing inside the horizon. It's always pointing towards smaller radii. So you always have to go towards smaller radii, and it gets worse and worse, and eventually it ends badly. So there is, at least according to classical general relativity, there is a singularity at the inside of this horizon, or at the center of this horizon. And so the statement that there is a horizon means that every observer, once you're inside this region, you're always going to end up having a bad day. And so this point here, this R equals RS, it's given as an expression here of 2g m over c squared. This is our point of no return. Once you fall in this radii or radius, you can't get out. And so I've given here a couple of actual numbers for the different Schwarzschild radii for, say, celestial objects we may care about. And okay, for these first two, you can immediately see that that's pretty small. So if we were to imagine that all of the density of all of the mass of the Earth was compacted into a sphere of this radius, I mean that you could like hold it in the, it's like that big. It's pretty small. Great. So I should say that, yeah, Schwarzschild, all of this information was secretly in Schwarzschild solution. It was there. People kind of saw it, but people mostly assumed that it was just kind of an artifact of this particular solution. And so I think the real importance came when we realized how collapse is often inevitable, or once you have a certain configuration, that forming a horizon and forming the singularity at the end of the day is always going to be the end game. And so it wasn't until probably, I'd say, around late 50s or so that people really started taking these horizons seriously. And once they did, that kicked off what we now know as the golden age of GR. And so one quick caveat here, I'm going to almost entirely throughout this talk ignore everything going on inside this horizon. Things get confusing and weird, and I think that will probably be confusing and weird enough without thinking about stuff inside the horizon. So there's all kinds of interesting questions there, but we will say nothing about them. So, as I said, once people started taking these black holes seriously, that kind of kicked off what we called, or what some folks call, the golden age of general relativity. And so we're going to quickly state some of the kind of key findings we had in this time era, and of course the royal we is not me, because I was not born. This is roughly somewhere around 50s to 70s, maybe mid 70s. So this is still pretty old news, but it's interesting news. So what are some curious facts that I want you to know about black holes? So the first thing you might want to do is ask, okay, I want to study a black hole, and to do this, I should, ideally, I would like to set up a lab, somewhere nearby the black hole, so I can like throw stuff at it, or I don't know, look at it with binoculars or something, whatever you want to do. And so the first question you should ask if you want to do these kinds of experiments is, how hard is it? How much fuel do I need to put on my rocket to sit somewhere close to the black hole, or roughly at the horizon? And this is an interesting natural observable in gravity, and it goes by the name of surface gravity. Pretty reasonable. Heuristically, it's kind of how much acceleration do you need to not fall in right around the horizon. And so that is what's meant to be depicted here, is we have our little friend here who's floating. I didn't draw his rockets. Maybe he has like rockets down here holding him up, but he's going to sit there and ponder black holes. Great. So once you have this notion in your head, you might ask, okay, well, I should probably try to figure out what is the best place to set up my lab so that I can conserve fuel. And here we run into our first fact, which is that, in fact, it's equally hard, no matter where you are in your black hole, to sit close to the horizon. So this fact has a slightly funny name I've given here, called the zeroth law, that we will see is interesting for other reasons later. But the statement is that the surface gravity is constant on the event horizon, that there's kind of no preferred place for you to sit around an isolated black hole. For this fact, this picture is very misleading because there's all kinds of junk. So these rings are really a bunch of matter that we should be ignoring for our purposes. But this was the coolest picture of a black hole I found. So that's what I used. And so once we, acknowledge this fact, it's like, okay, well, I guess I'll just, at least now I know how much fuel I need, and I can set up my lab, and I don't have to worry about, am I wasting fuel? Great. So once we have our lab set up, hovering around our horizon, we can start doing experiments. And the first experiment we're going to do is we're going to take some object, we're going to attach it to a string, and we're going to very slowly lower it into the black hole. So very, very slowly lower some mass into the black hole. And after some series of experiments that our friend has done, this is the benefit of thought experiments, is there's no budget, so we can just keep doing this forever. But our friend will drop this mass into the black hole, and he'll observe this relation here, which is somewhat plausible, that the black hole gets a little bigger. So I'm not going to scroll all the way back, but if we remember the Schwarzschild radius, which is the size of our black hole scales with the mass of the stuff inside of it. And so it seems reasonable that if I put more mass inside the black hole, then it'll get a little bigger. And that's really all the statement is, except you have to be careful how you do it. You have to do it very, very slowly, very carefully. Great. So we do this experiment a bunch of times. We get this result. We're happy. And then, we decide to get a little more adventurous. And now we just really start chucking stuff in. So we just really let it go. And the question is, what happens now? And after doing this experiment many, many times, what we see is that no matter what we do, no matter how we throw something into the black hole, or no matter how we really kind of do anything to the black hole, the area always stays the same or increases. And so this is kind of a surprising fact in general relativity. So general relativity is a bunch of complicated differential equations that describe kind of how space-time itself kind of reacts to matter. But at the end of the day, we really think of, like most equations in physics, they're kind of time reversal invariant, or something. Most equations, it's time going forward in time is roughly the same as going backward in time. And so the fact that out of Einstein's equations, a very non-symmetric constraint comes out is very surprising. And of course, this is really tied deep down to the irreversibility of a black hole to begin with, which is that once you fall in, nothing can ever get out. So this is kind of the manifestation. This is a manifestation of that irreversibility. And so these are three surprising facts, possibly, about black holes that folks found in the 50s, 60s-ish. And by folks, I mean folks like Stephen Hawking or his collaborators, and Carter, Bardeen, Wheeler. So all kinds of the heavy hitters in general relativity were really active in this phase of time where people were figuring out these curious features of black holes. So we have black holes, and I've quickly just summarized these three rules I've told you. Again, constant surface gravity. If I do things carefully, then mass increases proportional to area, and no matter what I do, area always increases, or stays the same. That's fine too. And maybe this looks a little familiar, and that's because these laws were thus named because they're very similar to things that we had seen before, which is namely thermodynamics, classical thermodynamics. So I think we are probably all reasonably familiar with the concept of a temperature, and what we call the zeroth law of thermodynamics is that in equilibrium, the temperature is constant throughout the object that's at equilibrium. Really, it's kind of, so that's the zeroth law. Temperature is constant. Then we have the first law. And in this case, it's a statement that, okay, this one's a little harder to picture, but it's relating, if I change say the entropy or the energy of the system, then how the other one has to react. And finally, so this is, again, a statement about this process is supposed to occur continuously in equilibrium, so it has to be an adiabatic process. That's similar to the fact that with our black hole, we had to drop something in very slowly. But yeah, so, and then finally, the second law of thermodynamics is pretty famous, which says that the entropy must always increase in any physical process in the universe. And so what is the entropy? As a quick reminder, what it's really doing is kind of quantifying how much we don't know about our system. So when I look at a gas canister or gas in this room, then obviously I don't know where each individual particle is. or what its speed is, but I know things like its temperature and its pressure. And so the entropy is kind of counting, how many states do I have for a given fixed macro state. And so these two pictures here are meant to illustrate that if I constrain all of the gas particles into a small corner, then there's obviously much less room. There's obviously more configurations like this than there are like this. And so we call this a high entropy state, a low entropy state. And the second law of thermodynamics says that gas always goes from left to right. It practically never goes from right to left. So the real point here is that these rules are meant to suggest an identification between these facts we had about a black hole and these facts we know from thermodynamics. So in particular, that the mass is like the energy, which Einstein had also already kind of suggested to us. So that's not so surprising. The more surprising ones are the fact that we can supposedly interpret a black hole as having a temperature and also an entropy. And so these facts are not obvious. They're very so I really can't give very concrete derivations of these facts, but we can at least explain what they mean. And so, actually, so before I get there, you should notice that, so we've suggested that temperature is proportional to the surface gravity, which is, so it's just kind of analogy with that kappa is roughly where that T is in the other equation. So they should be proportional. But in particular, we only need to fix one of these constants of proportionality because then the other one is fixed by the other laws. So I'm going to focus on Hawking radiation, which is the statement that these black holes, in fact, really do have a temperature associated to them. But to see it, you need a tiny bit of quantum mechanics. So these black holes, any black hole, we believe, should have should essentially emit radiation that can be seen by our distant observer. And it will appear as black body radiation with this temperature. So this kappa, again, remember, is some property of our black hole. It scales roughly like 1 over the mass for a astrophysical black hole, say. And yeah, so once we do this calculation, and again, by we, I mean Hawking, and it's a complicated calculation, but he found his answer. And once you have that, you can then fix what are the constants of proportionality for our entropy, and you end up with this funny expression that involves essentially every interesting physical constant we have in physics. So there's K Boltzmann, there's speed of light, there's G Newton, and H bar. So this equation's got everything. It's also an interesting fact that it's up to you whether you want BH to be Bekenstein-Hawking, which are the two of the people that proposed this understanding of this entropy, or whether you want to just call this a black hole entropy. That's your prerogative, but it's a curious anecdote. And so, yeah. So again, our observer out here, he is surprised because he was expecting to see a black hole. And so he instead sees all of these random quanta coming out that seem to be at this temperature. And you can plug in the numbers here and see what you get for, say, a black hole with the mass of the sun. And what we see is that, okay, that's a really small temperature, and this is a really large entropy. So observationally, I mean, you never want to bet against experimentalists, but seeing Hawking radiation kind of experimentally seems tough. I will just say that. And also this entropy is just astronomically large. This is supposed to be the thermal entropy of the sun as a classical thermodynamic object. It has some thermal entropy we can estimate, and this is 20 orders of magnitude larger. So I guess you can kind of guess from here, h bar is really small, g is really small. This is essentially the area in units of the Planck length. So the Planck length is real small, so the area in units of it is going to be pretty large. So here I've been focusing mostly on kind of what we call equilibrium properties of these black holes, temperature, entropies. But there's a much longer story, I should say, that also understood kind of what are the non-equilibrium properties of this black hole. And so in particular, we can associate things like a diffusion or a viscosity or a conductivity with the horizon of the black hole. Depending on how you throw stuff into it, it'll kind of form ripples on the horizon and they'll dissipate and do interesting things. Great. So, so far, I've just told you a bunch of statements about black holes and how they have a curious, they seem curiously close to what we are used to from, say, thermodynamics or hydrodynamics for kind of the non-equilibrium stuff. And so the question is, can we, how do we interpret that? What does it really mean to say that this black hole has this entropy? And can we think of it as kind of the honest thermo or hydrodynamics of some other physical system, or of some physical system, I should say. And so what happens is, well, now we're going to change gears here and start talking about duality. And I think the simplest picture to keep in mind with duality is, I guess I've seen kind of switch or shift for this terminology. I'm not sure what the claim is or what the real statement is, but for me, I'm just going to think about this picture. And I think this illustrates duality in the sense that, okay, it's clearly just a picture of a bunch of black and white pixels, but depending on how you look at it, how you think about it, you can see either the two faces or the base. And so the moral of duality that I want you to take away is that there are different ways of viewing the system, and sometimes they're useful, and sometimes they're not in particular. So a more concrete example that is almost literally exactly what is going on in every instance of duality in physics is that essentially it's just a change of variables. So we're used to when we have some integral over the xy plane, I can chop up the xy plane into Cartesian little squares, or I can chop them into little angular wedges. And the statement, these two are equal. Okay, so this is some theorem in math, but for our purposes, we want to think of this as a duality statement, that two seemingly different objects are actually computing the same number. And so, again, some things are, say, easier in polar coordinates versus Cartesian, or vice versa. And there are also other coordinate changes that would be terrible and you should never use them because they would make your life much harder, but they exist. So the point is really that the choice of variables is not unique, and sometimes there are good and bad choices. Another, just slowly inching towards more physical examples of dualities, and I think maybe one that folks are familiar with is if I take Maxwell's equations without matter, then if I substitute E goes to minus B and B goes to E, then what happens is you end up with the exact same set of equations. And so we say that there's a duality, that there's some choice between what I call electric and what I call magnetic fields. And so there are all kinds of fancier examples I'm not going to go into. But the point here is really, again, there exist different choices of variables. Sometimes they're good, sometimes they're bad. And they might not always be what you expect. And in particular, now we get to the real crux combining the 2 points I've made so far, which is that what we learned in 1997, thanks to really a lot of work leading up to this, but really Maldacena was key in pushing the conjecture, which is that certain types of gravity I put in here in a box. So it's a kind of, it's a symmetric version of it's a very symmetric box we put gravity in, which is really if you're familiar with some GR, it's a cosmological constant. So we turn on some negative cosmological constant for our gravity. And the statement is that this is secretly some other system that has no gravity. And so this is exactly like these dualities over here, or these change of variables, except it seems a little more dramatic because one side has gravity and the other side has no gravity. So yeah, and so what this really means is that any question about this particular theory of gravity, we can translate into some other question about whatever theory of non-gravity we have. So whatever this theory T is, the best understood examples are kind of like super fancy cousins of, say, the strong interactions or the standard model. I'm not going to worry at all about what T really is supposed to be. We're just going to think about black holes. Yeah, so any question about gravity secretly can be fed through our change of variables and turned into a question about T, and vice versa. And so if this was, this is a conjecture, and really, how do you test such a thing? Well, you need to be able to either compute on one side or the other, and the other magical property of this conjecture, which is maybe sometimes called conservation of difficulty, is that which side is easy and which side is hard kind of switch, or sorry, I should say that when one side is easy, then answering the question is hard on the other side, and vice versa. So in particular for us, we're going to be interested in, say, kind of these difficult phases of matter I started off with. And so these are going to be difficult. And so what this duality is telling us is that on the gravitational side, that they're in some sense easy. And so what I mean by easy is that on the left-hand side here, you can do just kind of literally classical evolution. And it'll tell you about interesting quantum properties of this theory T. So again, we have this duality that says gravity in, okay, this box that I'm not telling you much about, but this funny theory of gravity is secretly this other theory that has no gravity. But when we want to look at interesting questions on this theory T, it maps into something simple, hopefully, in gravity. And so going back to our black hole facts, what this duality is really telling us is that these laws of black hole thermodynamics and this funny theory of gravity are secretly identically equal to the laws of thermodynamics, the regular laws of thermodynamics we expect in any quantum system, that these laws are exactly the same as these laws over here. And so this is kind of one element of what we call the dictionary, which is how we map, what is the change of variables between the two sides. It's a very non-trivial change of variables, I should say. It's really complicated, and there's still tons of open questions. But yeah. So okay, yeah. The one benefit of this equality here is that it gives us some kind of a nice microscopic picture of the black hole entropy, which has been very confusing without this kind of duality. In general, people have been confused about what is the microscopic counting of the black hole entropy for decades. But yeah, so okay, I'm not going to go much into detail about how what the other entries in the dictionary are. There are a couple of statements here. Mostly, what I would like to do is tell you really quickly, kind of practically, what is this? What do we do? And the answer is we have our black hole. It's in a box. So here's the wall of our box. And what we do is we turn on an electric field. We connect a battery to the wall of the box. And this electric field will shoot photons into the horizon. And these photons will propagate their waves in the space-time. And so you solve a wave equation, and it goes from the wall to the horizon. and then it gets reflected, some of it, and some of it gets transmitted. And so the reflected bit comes back to the boundary, the transmitted bit falls into the black hole, and the black hole gets a little bigger because it has gained some energy from the infalling light. And so this dictionary is telling us that we call the response, the current that we measure in response to this electric field, we just say it's what do I receive? What is this blue photon coming up? That tells me what is the current I measure in T. And the fact that the black hole has grown means that I've produced entropy, which means that I have heated up the system a little bit. So we remember that what does really a resistor do? Well, when I pass a current through a resistor, it heats up a little, it generates entropy. And so the kind of gravitational picture of this is that a photon has fallen to the horizon and gotten a little bigger. So our statement of duality is that some classical black holes are secretly identical to finite temperature quantum systems. And so in the last, I guess, hopefully a minute or two here, I will try to quickly give some simple examples where I think these ideas have really taught us some interesting facts that, in principle, I think we could have learned without gravity, but gravity at least showed us the way much quicker because we apparently were not clever enough to find it on our own. So first, I should make contact with superconductivity, which I had mentioned before. And so really the question is, how do I get the photon to not fall into the black hole? So a superconductor is something that conducts electricity without generating any heat. And so the gravitational origin of the heat that is generated in this picture I had before, right? This picture of a photon falling in, a piece getting reflected back, and that's our current, and then our black hole grew. How do we prevent this from happening? Well, you just put something in the way. And so these holographic superconductors are, sorry, these black hole superconductors, I should say, have a little coating that I'm not going to say anything about, but its whole purpose in life is to prevent photons from falling in so that our black hole does not grow and it stays at the same size and there is no heat generated. Great. I should say that you can, in a technical sense, these are unconventional superconductors. So if you're a superconductivity person, when I say unconventional, I mean that kind of unconventional, as in it's not the superconductivity we've known. It's not our grandparents' superconductivity. It's more exciting. Okay. There's a lot of slides here. Great. So I don't really remember what the time was like, but
it's 5 till the hour, so go a little bit longer and then
yeah,
question.
Great. So I'm going to skip the hydrodynamics bit for now and get to just one last example, which I think is pretty dramatic. Another instance where black holes have really taught us a lot that I think we hadn't appreciated in general quantum mechanics, as just in general, is the role of chaos in a quantum system. And so there's been a lot of work on kind of classical chaos and understanding how initially very close trajectories can separate in certain systems very exponentially in time. And what black holes have done is taught us how to mock up a similar situation in gravity and turn this into a quantum observable that we can then understand purely from quantum mechanical manipulations. So I don't have any time to go into real detail about this, but this exponent that we have here, lambda, in our classical system has a quantum analog that we call the quantum Lyapunov exponent. This was the classical Lyapunov exponent. And based on arguments or intuition built from gravity, these folks had found a sharp bound for all quantum systems. So this is a really dramatic statement that any quantum system where you can define this lambda q here, it is always bounded. And I would credit this intuition or this result to at least partly being due to black holes. But these folks had all studied this problem in black holes before they turned to the purely quantum mechanical proof of this fact. So it is a purely quantum mechanical fact, but it was inspired by gravity. And so I'm not going to tell you how that looks in gravity, and I'll just quickly, we have the summary. So black holes have interesting features. And in particular, some black holes are secretly equivalent to non-gravitational systems. And really the whole idea here is that this is now a new test bed for all of the ideas we've had about other condensed matter physics or quantum information, which I had no time to say anything about, or other particle physics ideas. So I think it's any tool we have in other quantum systems, we can now just kind of try to understand in a black hole context, and it gives us a nice kind of geometric picture, but it also can give us new insights and tell us where we had the wrong intuition from looking only under certain streetlights. Okay, so I'm just gonna leave the future directions there, and I'll stop here.
All right, thank you so much, Dr. Ramirez, for the great talk. So if anyone has any questions, you could maybe pop them in the chat or raise your hand. We already have some questions in the chat, so I think we'll start there. So Laura asked, and she actually asked this back when you were talking about dualities. So quantum mechanics is just a coordinate system change to this gravity in a box? So I think she was just making sure she understood.
So no, it's a great question. So I would say that some quantum mechanics are a coordinate change away from some of this gravity in a box. So I think a really important open question is kind of which quantum mechanical theories have I should say, useful gravitational dual. Depending on who you talk to, some folks will say every theory, no matter what, has to have a gravitational dual. I'm not gonna throw my hat into that ring, but I will say that the fact that I could draw, simple pictures on the gravitational side really relied on some features of these theories T that are not super physical, I should say, right? So none of these results are of. Okay, I'm just gonna leave it there for now.
Great. So next, Julian asked. So he's asking about the non-gravitational side of the duality. So he says if there's not gravity there, then is space not curved, or is something else replacing gravity, or what do you mean by I think he's just asking, what do you mean by non-gravitational theory?
Right. So by non-gravitational theory, I would mean that, so of course, at the end of the day, we believe every theory in our universe is, every material or every system we care about technically there is gravity involved, but for many materials or questions of interest, gravity is just so much weaker that we can effectively ignore it. So we can imagine we kind of freeze gravity and consider a quantum system on a fixed geometric background. And so that is primarily what I meant by it.
Great. So next, Lynn is asking about the unification of quantum mechanics in GR. So, I mean, maybe you could just update on how that, applies here.
So I think there different people would probably give different answers to this question. I would say that in certain contexts, in particular when you're in this funny gravitational box, or when you're in a negative cosmological constant, we think we have a pretty good understanding of what quantum gravity means in that setting, at least kind of in kind of a perturbative sense, I should say. So if we kind of if G Newton is small, which we can cook up by picking T correctly, then we feel like we have a good idea of how quantum mechanics and gravity play together in this negative cosmological constant space. So whether or not we can translate those, our insights to, say, the gravity we experience in our universe is a different question that I will not speculate on. Other folks have. So for sure, people have different ideas all along these lines. But
great. Thank you. Are there any, I don't see any other questions in the chat. Did anyone else want to ask a question by unmuting? Oh, so there's one more question. Are there any predictions of this duality theory? Lynn asks.
So I think it depends a little on what you mean by predictions. So I at least partially count this bound on chaos as a, maybe not a prediction, but it was a result that was hinted to us by from these gravitational contexts. And so
I don't know if you saw, she followed up. She
did see this. Yeah.
So she was looking for testable things.
Testable things. So if you mean that, can I construct a theory T that we think, can I construct the theory T in a lab that is explicitly dual to some interesting gravitational theory? We aren't there yet, for sure, or at least not in a way that we can understand usefully. But my perspective here is more that that black holes can kind of show us, what are the other possibilities in, say, hydrodynamics or chaos that we hadn't realized before. And one thing I definitely did not have time to go over is this fact about hydrodynamics. Gravity taught us that there's a new term in our currents that we could write down in hydrodynamics that for some reason we never did. I don't understand exactly what happened there, but for about 50 years, we kind of ignored this term. We threw it away without a good reason. And then we found out, in fact, there is a really good reason to include it. And this has absolutely experimental predictions. In particular, there's recent work that's shown how transport on the edge of a quantum Hall system has dramatic consequences from kind of this anomaly. So it's not saying that quantum Hall is secretly a black hole. It's just that the lessons we learned from the black hole are directly applicable to a quantum Hall system. So I think predictable in that sense. So maybe that's not predictable.
All right, so I think we're 5 minutes over, so we'll stop there. So on behalf of the audience, I'll thank you. So thank you so much, Dr. Ramirez, for the excellent talk. So for the audience, thank you for coming. Next week, we'll hear from Dr. Satzinger, who works at Google, where they're working to try to build quantum computers. So that should be a really fun talk too. So thank you so much for coming, and thank you again, Dr. Ramirez.
My pleasure.